Professor Sekar Nethi, who's the Professor and Head, Department of Specialty Chemicals Technology, Institute of Chemical Technology, Matunga, Mumbai, India.
Good morning to everyone. The chairperson, Professor Sushant Banerjee, the co-chair, Professor Shakir Ali, Professor Indupal Kaur, my colleagues who gave the invited speech and then who are going to give the invited speech, and my friends. So I shall be talking about the near-infrared active colorants in cancer theranostics. Now, the near-infrared light has got a lot of advantages in medicine, which we will be seeing now. Now, first let me give a comparison of some of the things have been already explained by my earlier speaker. In cancer, I think early diagnosis is very important. And in therapy, the photodynamic therapy, we use light to destroy the cancer cells. In diagnosis using the near-infrared absorbing probes, we use a fluorescent molecule which we tag to an antibody or antibody, whatever it is. Then it tries to locate where the cancer cells are. If the same antibody is also conjugated with a drug, then as soon as we locate the cancer cell, we can use a different light or same light to or with a different intensity to release the drug there, so that we combine the diagnosis with therapy. So this is what it is. So here, my job here will be to talk about the fluorescent molecules which are already used in imaging and which can be used for the theranostic purpose also. Now, the near-infrared light has got a lot of advantages. I think this august audience know this. Just to have a link, so there is a reduced scattering, so you have very clean optics there in the near-infrared region, and the near-infrared light penetrates well inside the cell, and we don't suffer from the interference of the autofluorescence from the endogenous pigments. And we can design the dyes in such a way that we need the required wavelength of absorption or emission, and we can tune the size so that the pharmacokinetics also works well for us, and we can tune for the brightness. We can have dyes with the kind of quantum yield and the kind of the extinction coefficient what we need. And since near-infrared light is a low energy, so the other cells we are not going to disturb. So this is a very specific targeted, you can say it is a drug delivery combined with the diagnostics. So already we have quantum dots and the inorganic nanoparticles, and I think we saw, I think the earlier speaker told he has got carbon nanotubes which are fluorescent. So they also come under what is called the fluorescent compounds we can use. And the dyes are actually, those compounds have got the nanotoxicity is still a question, and the biodegradability of these the quantum dots is again still a question. So the near-infrared absorbing organic dyes, they are otherwise called as organic dots. They have a lot of advantages in the theranostic applications. With this background, we move on to the kind of dyes which are available in diagnosis and which can be tuned to have a theranostic application. So I have listed all the commercially important fluorescent dyes, which is not only in the cancer, any oncological lab. So say doctors use all these kinds of the molecules. The ICG is very famous, I think, almost. And all the other things are ICG analogs, but ICG is used in large amount. And if you look at the structure of ICG, I think I am a chemist by profession. We do synthesize a lot of dyes. And this ICG comes from an important intermediate, that is a beta-naphthylamine derivative. So beta-naphthylamine is a proven carcinogen. It was banned long back. So it comes from that. So what we do is we block the position of one position in the naphthylamine so that it becomes water soluble, so it becomes less, it's not carcinogenic. Then we convert into this particular dye. So this is used in large amounts. And as I told, we have to progressively move towards the near infrared activity. So ICG, I have listed here the absorption, emission and all. So it has got, I think, 780 to 785. We need the wavelength of absorption, which is little longer than this. There are some compounds which you can see here, which I got even beyond 800 also. Even again, if you want to have good brightness, we need to have a beta naphthylamine derivative. So we as chemists, we try to synthesize the dyes which do not use this kind of materials and save for dyes with near infrared absorption emission. So that is what I am going to talk about. And this again further properties of the first one, this indocyanin green. Other two things, they are all natural motifs, and there are many natural products which also have near infrared absorption, and we can make them to emit in the near far infrared light. Now, how we can achieve the red shifted absorption followed by red shifted emission? We use several strategies in the lab. We have made, I think I will be showing some of my own publications. We have made many dyes. As I was mentioning with the previous speaker, if the dyes contain a carboxylic acid, we have actually proven strategy where we can bioconjugate. We have prepared these dyes, but we did not have any collaboration with the cancer research lab, but we have done bioconjugation in a different context for sensing the molecules with low vapor pressure, particularly things like RDX, TNT and all. So that was a government project, and same strategy can be used here, because there we used TNT as an antibody. Here we have to have a monoclonal antibody, that's all. So the first strategy is, in an organic molecule, if you have got increased number of double bonds, you get the progressively shift of the absorption, and I have shown you some of the structures, and some of these were prepared by us in the lab. But these molecules, what I showed here, only this is to demonstrate that there is a progressive increase in the conjugation length leads to redshift. But if you want to achieve the near infrared emission, we have to have so many other things to do in the molecule. Any organic molecule with absorbing in the red or deep red or the near infrared region will have it reduces what we call as the donor pi acceptor system. You have a chemical functional group which pulls the electron, which we say acceptor, is a chromophore. The other one which supplies the electron, that is the donor, and in between there is a series of pi bonds which are conjugated. And the first strategy what we told is that we increase the number of double bonds as we have in the carotenes, phycophines, all with naturally occurring dyes. And in addition to that, we can rigidize the donor and acceptor. These are the systems which we have made in our lab. And you can see there are some in places there are some carboxylic acids also here which we can use for the bioconjugation. In one molecule has got an ester. So this is the second strategy. We rigidize the donor, and then again we rigidize the acceptor. The acceptor here is the quaternary nitrogen, tertiary nitrogen. It again leads to, this is one of our very recent publications where we have prepared a lot of near infrared active chromophores. The other strategy is to inculcate a sense of, this is very similar to the green fluorescent protein or red fluorescent protein which we have, they are all biocompatible, and there is a in excited state intramolecular proton transfer within the system. These are all the molecules which we have synthesized, and of course we can modify the red fluorescent protein to get the near infrared emission. So the same strategy can be employed. So now I have explained here how it happens. At the excited state, there is a proton, the hopping. So then the energy gap it comes down, and you have near infrared emission. So this again is one of the recent papers. Okay. So these are all some of the examples what have come out from our lab. You can also have the fret, where you don't chemically bind to the resistance, but if two dyes are situated within the Foster radius, then the donor receives the photon from the earlier molecule. That means, suppose if for argument's sake, if a molecule emits at 500, the next molecule will take that 500, and then you will have a Stokes shift. Again, it emits at 700 nanometers. Like that, we have a physical array of molecules. So donor acceptor array, so that we get the near. This is being practiced. These are some of the dyes which we have synthesized in our lab, which we have published. And with this, I conclude my talk. Actually, we need a good collaboration with where all these dyes can be tested. So I am looking for that. And we have already done the bioconjugation with the other antibodies, and we have 2 Indian patents granted where we use this along with the antibodies for sensing the explosives. So same strategy can be used for for realizing the theranostic applications. Thank you very much.